Hello friends and welcome to our first lesson, AP Calculus AB. We start in our textbook in actually chapter 2. Chapter 2 is all about this big word, limits. We'll talk about later what limits are and how they're going to help us. And it leads to one of the first big operations and vocabulary words in calculus called the derivative. So we start with section 2.1. And section 2.1 talks about the tangent and velocity problems. Really, guys, calculus is all about this big word here called change. How fast does something change? How fast did your position change? How quickly is the area changing? Calculus is all about measuring change. And today we're going to talk about how do you move from, say, just your average rate of change, meaning how far did you travel, divided by how long it took you to do it. Remember, that's just like average or average velocity or average rate of change. We're going to start there, but our goal is, can we get to instantaneous? How fast are you changing right now? The best way to think about it, guys, is think about your car. When you're driving your car, or your parents are driving, you're looking, you can find out what the speed of your car is by looking at the speedometer. And just looking at this guy right here, looks like the arrow is pointed at about maybe 54 miles per hour or so, I think. Yeah, that sounds about right. Now that's your instantaneous speed right here. That's what you are traveling, how fast right now. It's not telling you average. The speedometer is not saying, all right, so how far did you just travel in how much time? Which is the average. No, it's not doing that. It's telling you right now, instantaneous, go. How fast you're traveling right now. And that's what we're going to try to figure out, because that is calculus. All right, look down here. Here is your first big goal in AP Calculus. Are you ready? All right. My question for you, my friends, is, what's the slope of this line here? What's the slope of this line? Notice the line is touching the graph of f of x at only one point, at point P, right there. And remember from geometry days, if a line touches something in only one spot, it's called a tangent. So this is a tangent line. So let me rephrase my question then, friends. What is the slope of that tangent line at point P? No, we don't know. That's the thing. We don't know what it is. We don't know how to find it. And honestly, we don't know why we're trying to find it. All we know is that our first big goal in AP Calc is how do you find the slope of that tangent line? Once we do find out, then, oh my gosh, the doors that will open once we figure that out. Okay, so that's our big goal. We still don't know why, we still don't know how, but we're going to figure it out. Well, here's what we can maybe do. All right, let's not focus on this diagram yet, but that's our goal. Let's go to the diagram on the left. I bet you guys could figure maybe the slope of this line from P to Q pretty well. Now, P to Q makes a line that's not a tangent because it's touching in more than one point. We actually call this one a secant line. And we use that term from time to time. This is a secant. The other one over here, if you remember, was a tangent. All right, well, to find the slope of this secant line, for example, use the letter m from mx plus b, if you remember. Remember, you only need 2 points, and we got it. We got p, and we got q. It's just rise over run. So could you find the slope of that? Yes, you could. Absolutely. All right, well, we're going to cheat a little bit. I really want to find the slope of this tangent line over here at one point. We just can't do it because we can't find the slope at one point. It's not legit. You try to do the algebra, and you're going to end up dividing by 0. Trust me. So we're going to kind of cheat. We're going to start over here on the left-hand side and draw that secant line. And then watch what I'm going to do. I'm going to keep P, the point P, planted there. I'm going to nail it to the floor. And I'm going to take the point Q, and I'm going to slowly redraw him along the f of x curve here. And every time I bring him closer and closer, I'm going to draw a new line. Why don't you make your eyes come follow me over here to the right? This is exactly what we're doing. See how P, again, is planted here on the left, and we're going to sneakily move Q little by little. You're going to move him from here to here, new line. Let's move him a little bit closer, new line. A little bit closer, new line. A little bit closer, new line. Now, every time I'm doing this, the new line is still going through 2 points. So can I find the slope between those 2 points every time I do this? Oh, you betcha, you could. Absolutely. But the reason I'm doing that is if we can figure out what the slope is for this line and this line, and this line, and this line. Are you a believer? Do you believe that as I get really, really close, if point Q gets really close to point P, I could almost find this slope right here? Because if I take the estimates that I get from all of these slopes, all these slopes, I should get really, really, really close to that slope there. So that's how we're sort of cheating in a way, wink, wink, on how we're going to find the slope of the tangent line in the middle diagram. We're going to start on the left over here, make a secant line and find that slope. And then we're going to sneakily drag the Q point closer and closer to P and try to figure out what slope value am I getting really close to. I would love to show this in motion, but we'll have to do that when we're in class next time. So remind me and I'll do that. All right, let's play. Here's how we're going to do it. Don't worry about this chart on the top of the page yet, but can you just look at this diagram here in the middle? Here's another drawing of our secant line from P to Q, going through 2 points. But now look how I'm labeling the 2 points. Here's point P, which I'm using X subscript 0 and Y subscript 0, or just X sub 0, Y sub 0. And over here I have point Q, and point Q is point X sub 1, Y sub 1. All right, now if you were actually going to find the slope of that line between those 2 points, you would just do the rise over the run. That's it. Remember, rise is over here on the right-hand side. M, remember, is for slope. Sec is for secant. What is the slope of the secant line? Well, it's the rise, which is y1 minus y0, divided by the run, which is x1 minus x0. You remember that back from your algebra days. Okay, that's cool. But remember also, guys, a more adult-y way of writing these 2 points would be over here for point P. I can say this is x0, comma, yeah, the y value, but the y value actually is the same thing as the function value, right? So instead of saying y0, I can say, well, f of x0, right? That's the same thing. Do you believe? Because it is. Also over here, how about point Q? I could say point Q is the same thing as x1, comma, f of x1, right? So now if I do that, what's the rise really, really? Yeah, y1 minus y0 is still legit, but what if I wrote it this way? That's the new rise. Does that make sense? That's the same thing as y1 minus y0, and still, again, divided by x1 minus x0. So these two formulas right here are pretty much the same. I'm just writing it in terms of x's and y's, or x's and f of x's. All right, that's cool. So maybe I can just play with this for a little bit. Just these two equations for now. Let's see what we can do with that. Well, let's see. Let me fill out this chart over here. This chart you're going to see under Resources, Chapter 2. It's going to be called the Section 2.1 chart. So you can go ahead and download that and use that for your notes for today. But do you notice these same 3 diagrams I showed you before? This is where I got them. Okay, we're going to play with this and see if we can try by trying to fill out this chart here in the middle. Here's what's going on. I've got a function here, and I'm going to use the good old parabola x squared. I want you to find the slope of the secant lines between the point x equals to 1 and these x values that are all along this top row. So you can consider this as x1 up here, and all these values across the chart here are all x sub zeros. Okay, that's great, but don't we need the y values, right? Or the f of x values? Sure. Okay, so if this is x sub 1 is equal to 1, then what would the y coordinate be equal to? Or what is f of x sub 1 equal to? Well, what's our function? Oh, it's over here, right? So when x is 1, what is the y value? 1 squared is 1. Okay, so that's really my f of x1 value. Now, in order to find the f of x sub 0 values, that's what's going to be over here. This is the f of x sub 0 values. So as you plug each of these x values into your function up here on top, you're going to get your new y values along this row here. Okay, so once you're going to have that, you will have x1, x sub 1, check over here. You'll have x sub 0, check, new one. And you have f of x sub 1. Yes, it will always be 1. just like the x sub 1 will also always be 1. That's the one we're going to sort of staple to the floor, right? That's the x1 is always going to be 1 here. And the f of x1 will always be 1 because it was 1 squared in the function. So keep that constant. Don't change those. It's the ones up here on the top chart. These x sub zeros are changing. And therefore, these f of x sub zeros, or y values, are also changing. Okay, so once you know that, you'll be able to figure out what's the new rise, the f of x1 minus f of x0. What's the new run, x1 minus x0. And therefore, we can plug it into our secant formula and find the slope. Okay, let me start you out. Let's go back up here to this chart. Notice I just took sort of a snapshot of that chart and I put it up here. Okay, remember that the point we're starting with is x1, y1, and that was, x1 was 1, and the y value when you plugged it into x squared was also 1. So start with that and keep that constant. Now the x2, y2 will change depending on what you're doing on the chart. And right now, if we just start with the first one, let's try to enter the numbers here on this first column here. Okay, x sub 2, oh sorry, I used x sub 2. I should go back to x sub 0, Mr. Brown, my apologies. X sub 0, y sub 0. There we go, that's much better. Let's make x sub 0, 2. Now what is y sub 0? Remember the function was f of x equals x squared, right? So if x is 2, what is y? 4. There you go. When x was 2, f of x, the y value, is 4. And again, your brain, remember, you're telling yourself these are the x sub zeros here, and these are the y sub zeros. Okay, let's keep going. So what's the rise? What is y1 over here minus y0? Okay, well, y1 was over here, y0 is over here, so we can just do y1 minus y0, and I get -3. Sounds good. Let's do the run. Remember, the run is going to be x1 minus x0. And we got that over here. Here's x1, and here x0. 1 minus 2 is -1 in my book. All right. And then let's use our secant formula over here. You can use either one. There again, they're both the same, either the y's or the f of x's. And if we do rise over run, we would get -3 over 1, which is +3. Good. All right, so I know the slope of that secant line would be about 3. That's great. But let's bring this number closer and closer to 1 to see if I can figure out what the actual tangent slope will be. So we're going to keep going on this chart. I'll do one more with you, and then your job is to try to finish the rest of that chart all the way across to the edge on the right. Let's do one more. All right, here's our new x sub 0. Remember, x sub 1, y sub 1 is going to stay the same. We're going to staple that to the ground, and we're moving our point Q, or x sub 0, around. All right, my new x sub 0 is 1.5. If I plug that into f of x equals x squared, what is 1.5 squared? Me thinks it's 2.25. Therefore, what is the rise? How about y1 minus y0? That's going to be, how about -1.25? Let's do our run. That's x1 minus x0. That's 1 minus 1.5 is -0.5. Okay, why don't we do the secant slope? Let's do rise divided by run. And we get -1.25 divided by 0.5. I get about 2.5. And that's done. And keep going. Here's now your new x sub 0, and you're going to find your new y sub 0 on that chart. And keep going. You're going to notice that the secant slope is going to keep changing as I bring that point closer and closer and closer and closer to here. Here's our goal. So our goal is to try to figure out what is the slope of the line at 1. Because at this point, my starting point of P will be at x equals 1, and my ending point of Q will also be at 1. So we'll be at this special moment right here, where I've moved all the way over here, and we're going to try to estimate. We won't be able to really officially find the slope. It's going to be tough, and you're going to talk about that when you get to these problems here. So after you finish that chart, friends, go ahead and answer those questions there and see how you do. Good job. All right, before we end, one last question for you guys. Let's talk about velocity. All right, when we throw something up in the air, it generally makes a nice little parabola. It comes up and it comes back down. And we have this equation here, this formula for that parabola. There we go. This ball is being thrown up in the air with the velocity of thus, and its height after t seconds is given by this equation here on the right. Let's find a couple of average velocities. And what we're going to do is we're going to take our average velocities at a certain point of t equals 2, and we're going to keep sliding and sliding it closer and closer away so we can maybe find what the instantaneous is. So in our picture here, let's say my point is here, and I really want to find what is the tangent line at that point, friends. What we're going to do is we're going to sort of estimate by taking another point here and drawing it closer and closer and closer and finding all of these secant slopes. As I get closer and closer, what is my sort of estimate of what the orange tangent is going to be? That's basically where we're starting. All right, friends, here's part A. Ready? We're trying to find the average velocity. Average velocity, again, would be rise over run, the slope of the secant. So I need the x1, x0, y1, and y0. But here we're not using x's, we're using t's instead. So I'm trying to figure out when I'm beginning at t equals 2 and I'm lasting. Here's your tricky word, guys. When you're lasting, that means if you're lasting 0.5 seconds, that means you're starting at 2 seconds and you're going all the way to 2.5 seconds. There's your interval for t. That means we can call t sub 1 could be equal to 2.5 and t sub 0 could be equal to 2. So it goes on sort of an interval from 2 to 2.5. For example, just to look ahead on part 2 here, if I was to talk about starting at t equals 2 and lasting 0.1 second, that means you're going to start at 2 seconds and you're going to last 0.1 second. So you'll end at 2.1 seconds. There's your interval. So again, here will be t1 and here will be t sub 0. Now here's the problem. You have all the t's, that's not bad, but then what are the f of t's, meaning what are the y values equal to? Well, you've got a formula, right? So you're going to have to plug in all of your t values into that formula, grab your calculator, and we'll see what we can do. Let's start. Let's do part 1. If it lasted 0.5 seconds, we figured out that over here, t1 was 2.5, t0 was equal to 2. So what's the corresponding y1? What's the corresponding y0? Plug those in. I think after I plugged it in, I think I got a y1 of 0. Check that for me. And then I get a y0. When I plugged in 2 for t into the formula, I got a y0 of 16. All right, can we do the average? Let's do the average slope or average velocity of this now. Here we go. Back to our rise over run. That would be y1 minus y0 over x1 minus x0. All right, y1 is minus y0 is divide by x1, but if it's okay, it's really t1 and t0. So how about 2.5 minus 2? And I get about negative 32. Now, in AP Calculus, especially on the AP exam, they always want you to use units if it's a word problem or a real-life problem. So do make sure we use units here. Let's check and see. We're talking about the average velocity, and velocity is being termed in terms of feet per second. So there's our units for part 1 of part A. All right, let's try part 2. Same thing. So this part was, I'll put over here, part 1. This is part 2. If you get the gist now and you want to start working fast and work ahead, go right ahead and you can sort of do this on your own and speed ahead on the video and you can catch up with me. All right, let's do part 2. Again, rise over run. I want to find the average. I'm going to change the t's right away. Okay, so my new interval is here. It's 0.1 second. So it goes from, really, from 2 to 2.1. So that means t1 is 2.1 minus t0 is 2. When you plug in 2.1 in for t and you get y values, and you plug in 2 in, well, you already plugged in 2 in part 1, so you got that as answers. I think I got something like, again, check my math, friends. All right, so I divide that. I get about negative 25.6 units, please. All right, So right now it seems like the speed is kind of increasing. It's going from a very big negative number to a little bit less negative. Let's see what happens. Let's keep going. Now, can you figure out on your own, guys? Can you figure out what is this interval going to be? If I'm starting at 2 and I'm lasting 0.05 seconds, can you figure out the interval? Okay, good luck. Here we go. Here's part 3. Rise over run. What's the average velocity? Did you get it? Y1 should be 2.05. Oop, I put it on the bottom, sorry. T1 should be 2.05 minus your original 2. On top, when you plug them in, using calculator work, and I get my final average velocity here to be negative 24.8 feet per second. Notice what's happening. It's the number itself is going down, although the average overall value is increasing, but you see how it's slowing down a little bit. It's not jumping as far as it did before. All right, one more. Here we go. Part 4. You can do this on your own. This is lasting now 0.01 seconds. Average velocity. 2.01 seconds should be 2.01 minus 2. And up here, I should have the y value as well. I'm just going to jump all the way to the calculator, punch it all in, and I'll get negative 24.16 feet per second. How did you do? Did you get all these numbers okay? Some number crunching here and there. Now that's part A, and that's great. So now notice what happened. Go back to our picture up here. As I brought my blue secant line closer and closer and closer to where I really want to be at, the orange, can we estimate what the slope of the orange will be? Let's see. Watch what happens. When I was 0.5 seconds away, I have this. When I was 0.1 second away, when I was 0.05, I'm getting closer and closer to the number 2. When I was 0.01 away, I was there. So can you estimate about what would the actual velocity be instantaneous at 2? Well, let's see. From 32 to negative 25.6, negative 24.8, negative 24.16, what does it feel like I'm getting really close to? And there's a lot of different answers you can put, but I would say maybe the instantaneous velocity would be about negative 24 feet per second. If you said negative 23, that's also good, but I feel like it's getting really, really close to negative 24 feet per second, and that's instantaneous. So notice how we used average velocity, average, 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 and as I got closer and closer to the value I'm trying to make a tangent line, I get a really good estimate of what the tangent slope might be. For now, that's as best as we can do. But later, when we eventually do learn this big word up here, it'll be a lot easier. So that's going to be our big tool for later, but for now, we'll do in the best we can. And there is your introduction to section 2.1. Good job, everybody.